Hello everyone, my name is Carl. Welcome to my workshop and welcome to my YouTube channel. So, what's this next to me in the vise here? Well, you might remember about a year ago when I was at my brother's at Retro Mechanica, I spoke about how I wanted to do a turbocharger to gas turbine conversion project. Well, it's about a year later from when I made that statement, or perhaps 10 months now, and I've finally got round to making a start, at least at getting some numbers down. So what we're going to do in this video is have a look at some of the numbers and some of the calculations that we need to do to get this conversion done. And so this is the turbocharger that I'm going to be using. So I'll bring you in handheld now, and I'll show you some of its salient points. So this is the turbocharger that we're going to be using. As I just mentioned there in the intro, it's a T3 type turbocharger, and it's just a generic one made in China that I bought from a company here in the UK called Max Speeding Rods. As you can see, it's got a wastegate actuator on it, which we're going to have to remove to do this turbo conversion, or a gas turbine conversion I should say. And here you can see the oil outlet, and the oil inlet is down here, just where my finger's pointing there. It's a little bit inconvenient for me to show you that because I'm holding it in the vise by the turbine inlet scroll. So when we look at this, we can see here we've got the compressor inlet at the front. So we need to measure this, the diameter of this, to do some calculations for the size of the combustion chamber, and we'll get into that in a minute. And round the back, obviously, we've got the turbine outlet, which is where the wastegate actuator is. So this whole assembly, this whole blanking plate, if you like, will be coming off, and we'll make a new plate to cover up the hole inside there where the wastegate actuator operates the valve. But we'll talk about that some more in a minute when we remove this, and I'll show you that. So this turbo is a fairly small one, and I would imagine it's going to it would give us a 3.2 compression ratio for the ratio between the inlet air and the outlet compressed air that comes out of the outlet. If it was running at full speed, which would probably be something in the region of 100,000 RPM. I don't expect to achieve that kind of level, though. I think probably will be more in the region of 84,000, 85,000 RPM, something like that. And that should give us a compression ratio of something in the region of 2.2 to 2.5, I would imagine, just looking at figures for previous units that have been built with this size of turbo. So I'll get this this compressor scroll off now, and we'll get the wastegate actuator off, and we'll do some measurements on the compressor inlet scroll, and we'll do some calculations. So I'm just working on getting this wastegate actuator off at the moment. Just remove this bracket. Then we'll get the scroll off, and we can do some measurements. So once I've got this scroll removed, I'll bring you back and I'll show you what we're going to do. So here we are. Here's the compressor wheel with the scroll removed. Now, you probably know this already, but perhaps you've never seen one of these before. You don't know very much about turbochargers. What we have here is a compressor on the same shaft as a turbine at the back end. So we have a turbine driving a compressor on the same shaft, which is exactly what we have inside a gas turbine engine. So in theory, all we need to do to this arrangement is to add a combustion chamber, so that then we can generate some hot gas to drive the turbine, which then drives the compressor. Compressor forces more air into the combustion chamber, where the fuel is burnt with that air, and that produces more hot gas to drive the turbine, and we end up with a self-sustaining cycle. So I'm going to do some measurements now on the turbine, or rather on the compressor wheel. So we need to measure the diameter of the actual inlet area, which is the inducer here, then measure the diameter of the hub, and then from that we can calculate the inlet surface area, and we can also use those diameters to calculate fairly roughly, but good enough for our application, the size and dimensions rather of the combustion chamber that we need to make. So let's have a look and see what this diameter is of the wheel. Just zero the vernier. 2.077 inches for the wheel, and the hub is coming in at 0.733 inches for the hub. So we'll get over to the whiteboard shortly and we'll have a look at some of those calculations that I mentioned. I mean, these are, we're talking about, you know, they're approximate calculations, but they're going to get us near enough for what we need to do with this thing. So the next thing we'll do is we'll get this this plate off the end of the turbine and we'll show you that. Right, so I'm just removing this adapter plate off the end of the turbine section, which is for the wastegate valve. And I will show you that shortly. Hopefully my arms aren't in the way. I think you've got a reasonably good view of what I'm doing. And if you're not familiar with turbochargers, they are extremely interesting devices, and they're worth a bit of research. They've got some interesting history. So there we go. That's the there's the wastegate actuator there. So the reason we need this off is because I'll bring you in a bit closer. So your handheld now, usual disclaimer. There's the turbine section, which obviously is driving the compressor, and this hole here, under normal usage in automotive applications, this allows some of the exhaust gas to bypass the turbine, called the wastegate. But we don't need that for our application. We want all of the gas that we produce from the combustion chamber to drive the turbine, to drive the compressor. So what we'll do is we'll make a new plate to cover this section and blank this off, and to that we'll weld a short stub with probably a V-band flange on it that we can then connect some sort of a jet pipe onto to gain some thrust from the excess gas that comes out of the turbine. Because that gas, when it comes out of here after it's driven the turbine, it'll still have some energy, so we can use that to give us some thrust. Basically what we want is just enough energy to drive this turbine, and then we extract the rest in thrust through the nozzle at the end, the jet pipe as it's sometimes called. Right, so I've got you overhead again now, and you can see that I've rotated the scroll around about 90 degrees to put it in the same plane as the turbine inlet. That'll allow us to have a much easier path for the flow of the air into the combustion chamber, because the combustion chamber is going to be what's called a saw thumb combustion chamber. That means it'll stick up vertically from this turbine inlet, and that's basically it'll give the easiest flow path for the hot gases into the turbine. They won't have to go through any 90s or any sort of bend radii, which would reduce the efficiency of the flow, because if you put a hot gas or any sort of gas really through a bend, you get losses at the corner. So we just want that going straight through there, because the efficiency of our combustion chamber isn't going to be 100%. It probably won't even be 90%. It'll be something in the region of 70%. So nothing's going to be optimal on this design, so we need to get as much out of it as we possibly can. This is the oil inlet for the turbocharger bearings, hydrodynamic bearings in this turbocharger, which means that basically they run on a cushion of oil or a film of oil. So we will be pumping oil into this inlet here. It's got a small restrictor at about 40 psi. That's so that we don't get any issues with back pressure from the compressor or from the turbine gases driving the oil back into the back across the bearings. So in here at 40 psi, out at the bottom, as I showed you earlier on, now we need as unrestricted an exit for the oil there as we possibly can, and we're going to be looking at something in the region of 10mm ID line coming out of the bottom of there. straight back into the oil reservoir with no restriction whatsoever, just straight back into it. So the oil circuit into the turbocharger will include a cooler, because the oil supply to the turbocharger in this application, as a not just as a gas turbine, but in its application as a turbocharger in vehicles as well, the oil is acting as a coolant, and more especially in our case when we're using this as a gas turbine, because we've got hot drive gases driving the turbine. So the oil is also keeping the whole the bearings and the unit cool as well. So we'll have a cooler in the system. So we'll move you on now, and we'll go over to the whiteboard and we'll look at some of the numbers that we need to be interested in when we're building a gas turbine from a turbocharger. Right then, here we go. This is it, the bit you've been waiting for. You know, I know you love it, don't fight it. So I've written up here, look, turbocharger to gas turbine. So we know our compressor wheel diameter is 2.077 inches. Our compressor hub diameter is 0.733 inches. So we work out the areas of both of these and subtract one from the other. We end up with an inlet flow area of 2.96 square inches. And a very, very approximate calculation, that will give us a flow rate of about 0.705 pounds per second into the compressor. So our combustion chamber dimensions, we can also work them out from this. And these are all rule of thumb based on workable designs and on some theory as well. If we worked out using gas turbine theory, we could get really accurate figures, but we don't need to do that. We can just use these rule of thumb numbers that have been used in previous designs. So for our flame tube, which is the inside part of the combustion chamber where the combustion actually happens, our diameter of that needs to be, for a small turbo like the one we've got, 3 times the compressor wheel diameter. And our flame tube length needs to be 6 times the compressor wheel diameter. The outer casing of the flame tube that the flame tube sits inside of, the diameter of that needs to be about the diameter of the flame tube plus 1.5 inches, and that gives us enough gap inside there to be a nice plenum to allow the air from the compressor to flow into and get into the combustion chamber flame tube easily, without causing too many eddies or too many losses. So the fuel that we're going to be using, as it says up here, is propane. We're going to be using that not only because every other gas turbine turbocharger conversion uses that. It's relatively easy to get hold of, it's safe to handle and relatively safe to use, and the other thing about it is it has a very wide fuel to air ratio that it can cope with in terms of combustion. So even if we were to make a really poorly constructed combustion chamber, we'd still get it running with propane, as opposed to any other type of fuel that a gas turbine might want to use, like kerosene, for example. So the idea is we'll start off basically, very basic with this turbocharger to gas turbine conversion. We'll follow all the rules that everybody else has used, and we'll get it working, and then we'll try to refine it and use different fuels and go down different roads. But we just need to get it working first. So we'll go on now and we'll have a look at a little bit more detail of the combustion chamber and how it's constructed. So this is a very rough diagram of what our combustion chamber might look like, or the form it might take. So I've written up here the two important factors that we have to take into consideration. Our compressor wheel diameter is 2.077 inches and our flow area is 2.96 inches squared. So these are our constants. So from that, and going back to what we said earlier, we can say that the combustion chamber liner, or the flame tube, is going to be 6.2 inches in diameter and 12.5 inches long, because it's 3 times and 6 times respectively. The outer, or the outer casing of our combustion chamber, will be 7.7 inches. Now these figures are based on this number here for a compressor wheel diameter. We can alter these slightly to suit the tubing that we're able to get, and we're going to be using stainless steel exhaust tubing, so we can alter these sizes slightly to fit in with stock availability of tubing that we can get our hands on, and it won't affect the design too much. So here we have at the top of the flame tube what I've labelled up as a fuel injector, and I've just shown it as a tube. What this will be for propane will just be, as it is there, a simple tube with some radial holes drilled into it, just to introduce the propane into the combustion chamber. Now, I've got quite a bit of experience of designing fuel injectors for rocket engines and all kinds of swirl devices and other intricate ideas, but for this propane injection, all we need is some radial holes to get it into the combustion chamber. So you'll remember we said about 0.705 pounds per second mass flow coming from our compressor. Now, if we were to dump all that into this combustion chamber without thought for where it's going to go, it would simply blow the flame out and we would have no combustion whatsoever. So what we have to do is we have to split the combustion chamber, or the flame tube rather, into three sections: the primary, the secondary and the tertiary sections. And we have to remember that what we're trying to do here is to produce drive gas for a turbine. So we need to put some air in here in the primary section to actually create combustion, and 30% of the flow area we need here in the primary section to get air in to start the combustion and to actually sustain it. Then we put the rest, then we put the next section, the secondary section, we put in 20% of the air to complete the combustion. And then in the tertiary section, we put in 50% of our flow rate air to dilute the gases as they come down the combustion chamber flame tube, so that they're cool enough to drive the turbine once we get to this point. And you can see here I've labelled it to turbine. So 30% equates to 0.9 inches squared. If we compare it to this 2.96 inches squared flow area, if we take that, if we call that 3 inches squared to make the calculation simple, then we have 0.9 inches squared for our primary zone, 0.6 inches squared for our secondary zone, and 1.5 inches squared for our tertiary zone. And in the primary zone, we want fairly small holes here because we want a nice homogeneous mixing of the air with the fuel to create a nice combustion zone here in the primary area. And then we can go slightly bigger holes here to get the rest of the air in to complete the combustion. And then we need fairly large holes at the bottom in the tertiary section to get the rest of the air in, the other 50%, to dilute these gases to give us a nice cool turbine drive. So for example, 18 1/4-inch holes would give us 0.9 inches squared in the primary section. So that's what we do. We just select the number of holes based on this area that we need here. So you can see at the bottom of the diagram here, I've written from compressor. So the air from the compressor enters the outer of the combustion chamber, and then it flows into the holes. Now I'm going to say a few words now and draw it with another diagram about how I want this air to enter the combustion chamber, because I'm going to go against what most people do when they build one of these turbocharger to gas turbine conversions, and I want to explain why I'm going to do that. Now when you look at these turbocharger to gas turbine conversions that have been done on YouTube and online in general, you'll very often see that they recommend having a tangential entry of the air from the compressor into the combustion chamber. And what that does is it creates a swirling flow of air from the compressor into the combustion chamber, and that's meant to give a uniform presentation of air to the primary, secondary and tertiary holes, thereby giving us a nice uniform inlet of air to all three of the stations for the holes to allow the air into the flame tube. Now, at the end of the day, they have built working, functioning gas turbines from turbochargers, and I've never built a gas turbine from a turbocharger. And as they say, an ounce of practice is worth a ton of theory. But I think this is wrong, and it's not optimal for the scenario that we're in here. And the reason for that is that a swirling flow of any kind, be it air or liquid, always creates a depression in the center of that swirl. And I can prove that mathematically if you like, and I can do a separate video on that if you want me to do that. But if you think about when you pull the plug out of your bath and you watch the water going down the plug hole, you get that swirling flow, and the center of that swirling flow, there is a void. And that's what happens when you have swirling flow in any instance, be it liquid or gas. You always get a void in the center. So essentially what we're doing is, what we want in here is we want pressure to drive the air in through those holes so that it penetrates into the flow of the fuel and gives us good mixing and thereby good combustion. But what we're doing by introducing this swirling flow is we're giving us the opposite of that. We've actually got less pressure where we want it, i.e. at the walls of the flame tube. So what I propose to do in my design is to not have this tangential entry and to actually have a diffuser section coming from the compressor. So the base of the outer liner will be a cone like this, and then from the compressor the air will enter the combustion chamber at the bottom, and will run up either side of the flame tube, so that we don't have any swirl, and hopefully that should give us a decent entry of the air into the primary, secondary and tertiary sections. And also what I've drawn here is, I forgot to mention on the other diagram, there is going to be an expansion joint between the flame tube and the outlet to the turbine. So as I say, practice is obviously on the side of this design, and it seems to work for other people. But I want to try and do it this way because I feel that this is actually counterintuitive in terms of the what we actually want for the pressure conditions inside the combustion chamber. This is giving us the opposite of what we actually want. Alright, so we've come to the end of this very brief video just on the introduction to converting a turbocharger into a gas turbine. I hope it's whetted your appetite for the videos that are to come on the subject. There's going to be a lot more. We'll have to go into a lot more detail in the design of the combustion chamber, the lubrication system, the fuel injection system, and so on and so forth. Now, if you're watching this video and you're not subscribed to me, please consider doing so, because it really helps me. It really makes my day actually to know that people are watching me and people are enjoying these videos. If you are subscribed already, then thank you very much indeed for giving up some of your time to sit and watch me messing around in my little home workshop, and thank you very much also for taking the time out to give me a comment and to give me a like. So until we meet again, take care of yourselves, and I will speak to you soon.